China's Tiangong station just achieved what seemed impossible, cutting fuel consumption by 90% while the ISS burns through 800 kilograms annually just to stay in orbit. This electric propulsion breakthrough isn't just impressive engineering, it's reshaping the entire future of space stations. But here's what's really remarkable. We'll reveal how this Hall effect thruster technology works and why the aging ISS simply can't compete. Let's dive right in. When most people think about keeping a space station in orbit, they imagine rocket engines firing briefly to nudge it back into position. But China's Tiangong station has fundamentally changed this equation with a technology that sounds like science fiction. Electric propulsion that uses charged particles moving at 30 times the speed of sound. Here's the technical breakdown that's got NASA taking notes. The Tianhe core module houses 4 Hall effect thrusters, each operating between 0.5 to 10 kilowatts and producing 80 millinewtons of thrust. To put this in perspective, that's roughly the force of holding a piece of paper in your hand. But in the vacuum of space, this gentle push becomes incredibly powerful over time. The engineering elegance lies in the physics. These thrusters ionize xenon gas and accelerate the charged particles using electric fields, creating that characteristic blue glow you might have seen in photos. The particles exit at velocities exceeding 30 times the speed of sound, far faster than any chemical propulsion system could achieve. And here's what few people realize. This isn't just about efficiency. It's about fundamentally changing how we think about orbital maintenance. Traditional chemical thrusters on the ISS face a brutal reality. Without constant fuel resupply, the station would plummet back to Earth. The ISS burns through approximately 800 kilograms of chemical fuel annually just to maintain its orbit. Tangong's electric system reduces this to a fraction, saving up to 800 kilograms per year in chemical fuel consumption while dramatically extending operational capability. The Chinese Academy of Sciences solved 2 major historical problems with electric propulsion. First, the low thrust issue, by clustering 4 medium-power thrusters and operating them continuously rather than in short bursts. Second, the erosion problem that typically destroys ion engines over time. They developed magnetic shielding that repels damaging particles away from engine walls and created ceramic materials that withstand extreme heat and radiation for extended periods. But here's the data that really matters. Without electric propulsion, Tiangong's altitude would drop 30 kilometers in just 100 days. With the system active, that decay rate plummets to only 7 kilometers over the same period. We'll come back to this point later because the implications extend far beyond just one space station. The system's design for maintainability represents another breakthrough. The gas storage modules can be replaced in orbit using robotic arms, something that's never been attempted before on this scale. This makes Tiangong the first space station in history designed for long-term electric propulsion maintenance in orbit. But this is just the beginning. What's really surprising is how this technology positions China to dominate the next phase of space infrastructure development. This achievement represents more than an engineering upgrade. It signals a fundamental shift in how spacefaring nations approach orbital infrastructure. While the ISS represents the collaborative approach of the 1990s, Tiangong embodies 21st century efficiency thinking applied to space engineering. The competitive landscape reveals stark contrasts. The ISS, now 26 years old, carries over 100 tons of what has essentially become dead weight in its massive truss structure. Originally designed to solve the Soviet-era Mir station's power problems, this truss-based architecture made sense when solar panel efficiency hovered around 15%. But modern technology has made this approach obsolete. Here's where the numbers tell the story. The ISS generates about 120 kilowatts after recent upgrades, requiring enormous solar arrays that now overlap and block sunlight from reaching each other. Tiangong achieves nearly the same power output, 100 kilowatts, with only half the solar panel area, and that's operating at just 50% of its design capacity. The economic implications ripple through the entire space industry. Traditional space station maintenance requires constant resupply missions, carrying fuel, spare parts, and consumables. Every kilogram launched to orbit costs thousands of dollars, making fuel-hungry stations like the ISS increasingly expensive to operate. Tiangong's electric propulsion system directly addresses this cost spiral. And here's what most overlook about the timing. NASA has already announced plans to retire the ISS later this decade, partly due to these escalating operational costs. Meanwhile, China's station is designed from the ground up for decades of operation with minimal resupply requirements. The standardization advantage compounds these benefits. The ISS uses at least 5 different docking systems: SSVP, CBM, APAS 95, and others, reflecting its piecemeal construction by multiple nations over decades. Tiangong uses a single standardized interface called GNCI for all connections. This isn't just elegant engineering, it's strategic thinking about scalability and future expansion. But there's a detail most people overlook in this comparison. Tangong can function as a refueling hub for other spacecraft. When a cargo ship docks at one end and another spacecraft at the other, propellant can flow through the station to refuel visiting vehicles. This capability transforms the station from merely a destination into a service provider for deep space missions. The strategic timing couldn't be more significant. As commercial space stations from Axiom Space, Blue Origin, and others prepare for deployment, they're all studying Tiangong's innovations. The Chinese have essentially provided a real-world testbed for technologies that the next generation of stations will need to incorporate to remain competitive. And here's why this changes everything for the future of human space exploration. The implications of electric propulsion for space stations extend far beyond fuel savings. They fundamentally alter the economics and possibilities of permanent human presence in space. What we're witnessing isn't just an incremental improvement, but the emergence of a new paradigm for orbital operations. Consider the cascade effects. When a space station can maintain its orbit with minimal fuel consumption, mission planners can redirect cargo capacity towards scientific equipment, life support improvements, and expansion modules instead of propellant. This shift enables larger, more capable stations without proportional increases in launch costs. The maintainability aspect opens even more intriguing possibilities. If electric propulsion components can be serviced and replaced in orbit, future stations might never need to be abandoned due to propulsion system failures. We're potentially looking at space infrastructure designed for multi-decade operation with periodic upgrades rather than complete replacement. But there's a challenge that requires honest assessment. Electric propulsion isn't suitable for all orbital maneuvers. Emergency debris avoidance still requires the instant thrust that only chemical systems can provide. The Chinese engineers recognized this limitation and maintained chemical thrusters alongside the electric system, a hybrid approach that maximizes the benefits of both technologies. The scaling implications become fascinating when we consider lunar and Mars operations. Electric propulsion excels in the vacuum of deep space, where the gentle but continuous thrust can build up enormous velocities over time. Stations serving as waypoints to the Moon or Mars could use similar systems for station keeping and even trajectory changes. What happens if this technology proves as reliable as early results suggest? We might see a fundamental shift in how space agencies and commercial operators design future missions. Instead of fuel-constrained operations lasting 15 to 20 years, we could be looking at space infrastructure designed for 50-year operational lifespans. And here's what's truly noteworthy about the timeline. China didn't just develop this technology, they deployed it operationally on their primary space asset. This represents a level of confidence in the system that suggests years of ground testing and validation we haven't seen publicized. The fact that they trusted this technology with their flagship space program indicates maturity levels that competitor nations are still working to achieve. The ripple effects are already visible. NASA's plans for future space stations increasingly emphasize efficiency and sustainability, principles that electric propulsion directly enables. Private companies developing commercial stations are incorporating similar technologies into their designs, though none have yet achieved operational deployment. The most significant long-term implication may be the democratization of space station operations. If maintaining orbital altitude becomes dramatically cheaper, smaller nations and commercial entities could afford to operate their own space platforms. This could accelerate scientific research, commercial development, and even space manufacturing in ways we're only beginning to understand. The Chinese have essentially proven that 21st century space stations don't need to follow 20th century design assumptions. As we move toward a future with multiple commercial space stations, lunar bases, and Mars missions, the lessons learned from Tiangong's electric propulsion system will likely influence every major space infrastructure project for decades to come. This isn't just about one space station's efficiency improvements. It's about rewriting the fundamental economics of human space exploration. This is exactly why China's electric propulsion breakthrough represents the most significant shift in space station technology since the ISS first launched. What this means is that we're witnessing the end of fuel-constrained space operations and the beginning of truly sustainable orbital infrastructure. The biggest insight here isn't just the 800-kilogram fuel savings. It's that China has proven space stations can be designed for multi-decade operations with minimal Earth dependency. This fundamentally changes the economics of human space exploration, making permanent orbital research facilities and deep space staging posts economically viable for the first time. This positions us at a critical inflection point in the space race. While the ISS represents the collaborative past, Tiangong demonstrates the efficient future. NASA's commercial space station program and private companies like Axiom Space are already incorporating these lessons into their designs. But China's operational advantage could last years, and this is just the beginning. The next decade will see multiple commercial space stations launching, each trying to match or exceed Tiangong's efficiency. The real competition isn't just about who gets to orbit first, it's about who can stay there longest and most cost-effectively. How do you think this electric propulsion advantage will impact the timeline for lunar bases and Mars missions? Will this push other space agencies to accelerate their own advanced propulsion programs? This is Space Core, and we dive deep into the engineering breakthroughs that are reshaping human spaceflight. If you want more analysis like this that goes beyond the headlines, hit subscribe. For the latest space developments that actually matter, you know where to find us. The age of sustainable space infrastructure has officially begun, and we're just getting started. SpaceX shocked everyone by launching Starship 37 with hundreds of heat shield tiles missing on August 24th. This isn't an oversight. It's a calculated risk to unlock 250-ton payload capacity. Why would they expose a $3 billion rocket to 1,600 degrees Celsius temperatures? The answer reveals their secret strategy for revolutionizing space travel costs. We'll uncover the 3 hidden experiments behind those missing tiles and how this risky move actually accelerates Starship's path to rapid reusability. Let's dive right in. When SpaceX rolled Starship 37 out of Megabay 2 last week, engineers worldwide did a double take. Hundreds of ceramic heat shield tiles were simply gone, not damaged, not delayed, but deliberately removed from the body and all 4 flaps. And here's what few people realize. This wasn't a last-minute decision, but a calculated experiment designed by hundreds of SpaceX's top engineers. The official statement from the SpaceX's Flight 10 update reveals their true intent. A significant number of tiles have been removed from Starship to stress test vulnerable areas across the vehicle during re-entry. Think of it like crash testing a car, except this crash test happens at 7 kilometers per second in a plasma inferno, reaching 1,600 degrees Celsius. But why would they risk a $3 billion vehicle this way? The answer lies in 3 critical engineering objectives. First, they're deliberately creating hotspots on the vehicle's surface, especially around the trailing edges of flaps, areas that experience maximum dynamic pressure during re-entry. It's like purposely removing armor from a knight to see exactly where the sword strikes hardest. The engineering challenge here is immense. Starship's stainless steel skin is less than 4 millimeters thick, thinner than most smartphone cases. During re-entry, this thin steel must withstand temperatures ranging from minus 270 degrees Celsius in space's shadow to over 1,600 degrees during atmospheric entry. Previous flights revealed hot spots that led SpaceX to redesign tile edges into smoother shapes, reducing friction drag. Second, SpaceX is testing their philosophy of resilience over perfection. NASA's space shuttle required manual replacement of thousands of tiles after each flight, a costly, time-consuming process that made rapid reusability impossible. Each ceramic tile cost $3,000 and represented a potential failure point. The Soviet Buran program actually failed partly due to similar thermal protection challenges. We'll come back to this point later, but SpaceX is producing Starships at their Starbase facility with the goal of manufacturing 1,000 vehicles per year. That's more than 2 per day. For this scale to work, their thermal protection system must be robust enough to handle occasional failures without catastrophic loss. Third, and most importantly, they're testing revolutionary metallic tiles with active cooling systems. These aren't random removals. In specific areas, ceramic tiles are being replaced with metallic alternatives made from stainless steel or nickel-chromium alloys like Inconel. Some even use liquid methane, sweating for active cooling, similar to how humans perspire to regulate temperature. The data shows metallic tiles are 3 times stronger than ceramics and can handle temperatures up to 1,650 degrees Celsius without frequent replacement. UK-based Spaceforge has already developed the Pridwin tile, an origami-style metallic heat shield that unfolds during re-entry and can last multiple flights without replacement. But this is just the beginning. What's really surprising is how this risky experiment connects to SpaceX's ultimate vision for space exploration. This missing heat shield experiment positions SpaceX at the forefront of a fundamental shift in spacecraft philosophy. While traditional aerospace programs treat every test flight as a potential disaster, SpaceX treats each mission as a controlled experiment. Even if Ship 37 burns up during re-entry, they'll consider it successful if they collect the necessary data. And here's what most people overlook. This approach is reshaping the entire competitive landscape. Boeing's Starliner required years of delays and cost overruns for relatively simple orbital missions. Blue Origin's New Shepard